This presentation discusses data preparation for your data modeling projects. This graphic is a brief overview of the CRISP-DM process. The data preparation phase is going to come after we have some understanding of our data, which will lead to our exploratory data analysis. So we have some data that we are trying to predict an outcome, and in this case we're looking at default. And we use data to learn a model, and so here is our question. We have two options. Do we, one, learn the model on all of the data and evaluate it on parts of the data, or do we split this data, set the two parts, and learn a model on one part and evaluate the model on the other part? Hopefully by now you know that we want to split our data into two parts and learn a model in one part and evaluate the other part. So you never ever want to use your testing data to learn your model. But to be clear, once you have already selected your model and you have validated it, made sure that it wasn't overfit, and then looking at it working the way you had expected, then that final model that we deploy, we will go ahead and train that model using all of our data. But when you're looking at just the data mining task and trying to identify the best model to use, we always want to train our models on the trained data set and then evaluate the model on the test data set. Doing data mining can look a lot like cooking. So we have a collection phase where we aggregate all of our data. That may include a lot of data merging and combining different data sets. Then we must clean our data. We may have outliers, missing data, and other things of that nature that we will have to address. We may need to integrate our data, transform our data, and then once we have done all of that, then we get to do the fun part of the analysis. But how much time do we spend on that preparation? You actually get to spend most of your time in this phase, in the data preparation phase. You may spend 60 to 80% of your time doing this part as part of your overall data mining project. So it's going to take a considerable amount of time. So there are different types of data preparation methods that you might employ. One thing is you have to figure out what to do with your missing data, and we'll talk about that. There are problems with outliers and the negative effect that they can have on biasing some of the inferences that we would want to make from our results. There's the handling of categorical data variables. What do we want to do with those? What do we want to do with our numerical variables? Sometimes we need to do transformations, and so there's a lot of different things that we need to keep in mind when we're putting our data together. So let's start with missing data. Data is not always available, and missing data may be due to various reasons. It may not have been entered due to a misunderstanding, or certain data may not have been considered important at the time of entry. It could have been accidentally deleted. Missing data may carry some information content. For example, a credit card application may carry information by noting which field the applicant did not complete. So what they did not complete can be informative about that particular customer's application. One of the things that we can do with missing data is we can ignore it. But we need to keep in mind if it affects a lot of records, we have a problem. So for example, in a data set of 30 variables, if only 5% of the ballots are missing and it is spread randomly and independently among examples and variables, you could have 78.5% of the records that you have that need to be removed. So if you do the math, you have 1 minus 0.05 raised to the 30th, that's going to give you 0.215. 1 minus 0.215, that's going to give you 78.5. So you may have to remove a very large portion of your data if you take this approach. So that may not be a great idea because you're taking a lot of the signal out with that as well as the data. So you can ignore the attributes with missing values, and then you may leave out some very important attributes that may actually be very useful in your predictive modeling. Another way to handle data is to infer those missing data. You can use a global constant to fill in missing values. For example, you can just say it's unknown. Or you can even attribute the mean for all samples belonging to the same class and fill in those missing values. For example, you could be looking at age. You take the mean age when the default is yes, or the mean age when the default is no. So if it is no, you should take the mean for those who did not default, and if it is yes, you take the mean age for those who did. But are other more sophisticated methods that you can apply. A lot of them involve using some algorithm to predict that missing value, and then using that as the predicted missing value and based on some model that you develop. An example would be using the k-nearest neighbor algorithm. You would use the k-nearest neighbor to identify other similar observations that have similar characteristics, and use the nearest neighbor to infer what that missing value would be, and just as one example. One thing to be very cognizant of is that with missing data, no matter what technique you use to conquer this problem, it's going to come at a price. So the more guessing that you do, the further away from the real data you're going to get. And this in turn can affect your accuracy and the validation of your data mining results. So just keep that in mind, that there is a price to be paid by making inferences on your missing data. As far as outliers are concerned, outliers are values that lie far away from the bulk of your data. Data that lie within 1.96 standard deviations comprise 95% of the area under the normal curve centered around the mean. So using the empirical rule, anything beyond 1.96 standard deviations about the mean is considered to be an outlier. However, depending on the applications and the size of your data set, it can be common to use 2 standard deviations as your benchmarks, 3 standard deviations, and if you have a really large data set, it can be even acceptable to use 4 standard deviations about the mean. But 2 is pretty common because 1.96 standard deviations is a very precise number, and 2 is just a lot easier to use in calculation. So there's always going to be some extreme situations that are inherently maybe extreme outliers, but they can be valid observations too. So among them could be, for example, the Black Monday of 1987, where they had one of the largest day drop in the market, or even more recently, the number of layouts we saw in March of 2020. It's highest by multiples that we've ever seen. But these are still valid observations. These are events that occurred. They weren't erroneously included into your data set. And so they're just outliers. So one of the things to keep in mind is when you see an outlier, you need to evaluate to see if they're a valid observation. Sometimes they need to be removed, but sometimes they don't. Another thing we have to keep in mind, especially with regression, is that some assumptions that we make on the error terms themselves. So for example, in regression, we assume that the variance of the errors is going to be constant throughout the predicted values. So outliers can often destabilize the variance of the errors in the model, and this can lead to bias in our estimates. So an example of that would be in multiple linear regression. If we are trying to estimate the income of the individual we are using as a predictor to try and infer how much a 1-year increase in age will affect that individual's income, that is an inference where I'm trying to relate age to income. The coefficient that I come up with in my linear regression is then an inference that I'm trying to make as the relationship between those two variables. Now, if I find that the regression model that I fit has the variance of the predicted values where the variance is not constant, then that inference that I'm making could be biased and therefore incorrect. So I would care about that in this situation and may want to consider fixing that. So let's talk about some of the useful variance stabilizing transformations that you can use. In this case, on the left here, we are looking at the relationship of the variance relative to your expected value of y. So in this case, if your variance is constant, then in this case, you do not need to do any transformations. You're good to go. Now, if your variance is equal to your expected y, so typically in this case, you would want to take this forward, and then you will see that in this case, this is going to be very prevalent when you're looking at Poisson data. Remember, Poisson data is typically going to be attributed to count data. So how many children someone has will follow a Poisson distribution. The relationship with variances is equal to your expected value of y times 1 minus your expected value of y. Typically, your arc sine would be a good transformation. And then, though more common ones you will see is if you see some from an exponential relationship, or in this case where the variance seems to be just a little off, then you may want to consider taking the log. Taking the log tends to be a good transformation for that. If you see that the relationship is, as noted here, the expected value y to the third, then taking the reciprocal square root is a good approach. Another one is reciprocal of the last one, but sometimes it's just easier to look at this on a graph. So let's take let's take a look at some of these graphs here. How do we go about making something a linear function or a linearizable function? In this case here, we're looking at A, B, C, and D with 4 charts. In this case, for the first one, some other options that you could have is to take the log of x and the log of y. And so that would fix these types of problems that you're seeing here. In this case, if your beta is greater than 1 or less than 1, which is kind of what we see here, then typically in this case you'd want to take the log of x and your y, and that would fix the problem that we see here on top. If you see this kind of relationship here where it is not linear and it looks a little bit more exponential, you can simply just take the log of one side, and that would tend to fix the relationship that you have. And so here are a few other ones. If you see this type of relationship up here on top, typically just taking the log of x can fix that problem. If you see this type of relationship that we have here on the bottom, then taking the inverse of 1 over x and then set y to equal 1 over y, that will tend to fix this positive and negative curvature that we see here. And if you summarize and look back at the graphs, here's the function that you start out with, a, b, c, and d. As the functions, and then so on. So then the transformation that you do for your y and for your x. And then you end up with your linear form of your transform function, where you can see written here in the far column on the right. But for our purposes, a lot of the things that we will look at, typically taking the log of the variable is going to solve a lot of your problems. So you will be able to just visualize that by doing a quick scatter plot of the transformed variable and looking at the relationship there. But remember, there are multiple types of transformations that you can apply if you try to create a linear form that's going to equalize that variance and lead to a more unbiased estimate of your coefficient. So now let me ask you a question. Given this distribution below, where you are looking at the market value of a firm versus the annual sales, the higher the market value of the firm, the higher the annual sales. You can see that there is an exponential increase in the sales as the market value of the firm increases. So given this distribution, what would be a reasonable transformation for the market value? So give it a minute to answer the question. If you need, pause the video. Here you will want to take the log of the transformation, and taking the log transformation will generally linearize this exponential relationship that we see here. So again, a log transformation can solve a lot of these problems that we have with unequal variances. So it's very common to use, especially when you are working with financial data. So definitely make sure that you're evaluating the exploratory portion of your project. So what do we do with numerical values? One of the things that we will see is that we will often want to do a normalization or a standardization of our numerical values. And what this does for us is it prevents attributes with large ranges from outweighing the attributes with small ranges. It brings all the variables with onto the same scale. Some of the data mining algorithms will specifically require that the data be normalized for them to work, but normalization is not generally required. So we will need to consider that, and we will be talking about which types of models will require normalizations and which ones don't. One thing is that a decision tree model can work well without normalization, but there will be a lot of them that don't. So for example, the Cain-Harris neighbor clustering and principal component analysis require that we normalize our variables, as well as several other algorithms like neural networks and other types of algorithms will require that normalization. So in handling that numerical variable and to normalize them, how do we do that? We're going to transform the data by converting the values into a common scale with a mean of 0 and a standard deviation of 1. This is the z-score. What the z-score tells us is how many standard deviations from the mean the observation is within the distribution of the observed values. And so we do that by computing this normalized variable, or again, we're trying to take this variable minus the mean and divide it by the standard deviation of that variable. And again, here where we get v bar and the standard deviation bar are the mean and the standard deviation of the variables. So remember, an observation that is more than 3 standard deviations away from the mean is absolutely going to be an outlier. And generally, using the empirical rule, anything beyond 1.96 standard deviations from the mean can be considered an outlier. So let me ask you this question. What is the z-score in this situation? So let's suppose that the mean of the standard deviation of the values for income variables are 54,000 and 16,000 respectively. With the z-score normalization and the value of 73,600 for income, what's that going to get transformed to? So take a moment, pause the video, and transform this to a z-score and figure out what your answer will be. So when we complete this calculation, we get a value of 1.225. So you take the survey, $73,600, which is our observation, minus the mean, so that's $54,000, and divide it by the standard deviation of $16,000. So this value will now become 1.1225. So with that, I'm going to leave it here. I hope you have a great day. We'll pick it up with some more discussion following a little bit more of your practice.